In this question from JEST 2023, we have a cylinder of height L and cross section A, which is placed vertically along the central axis. So we have this height is equal to L and its cross sectional area is A, and inside the cylinder there are particles, non-interacting particles of mass m. Each of these particles have mass m, and the gravitational force is acting on it downward, which is mg. Now the system is maintained at a temperature T. So this whole system, it is maintained at a temperature T. This whole system, it is at a temperature T. Now the question here is to find the ratio Cv at T tends to 0 to that of Cv at T tends to infinity, where Cv is the specific heat at constant volume. Now Cv is obtained by del by del T of average energy, and average energy is equal to minus of del by del beta ln Z. Here Z is the partition function. Z is equal to e raised to summation over r e raised to minus beta er. But we will not use this formula here because the energies we have here is not discrete. We have continuous energies. Therefore, summation becomes integration. Z is equal to integral, and we integrate over phase space because each point in phase space represents a particular state. Integral d cube p, integral d cube r e raised to minus beta h or e. So Hamiltonian or energy, it is equal to, let's use E itself. E is equal to px square upon 2m plus py square upon 2m plus pz square upon 2m. Because the particle is in 3D, we have these three terms of kinetic energy, and plus mg z due to gravitational force downward. So Z is equal to 1 by h cube. D cube p is dpx dpy dpz. So we have integral dpx e raised to minus beta px square upon 2m. So we are separating each integral with respect to x, with respect to y and z. This is from 0 to infinity. Then we have integral in y dpy e raised to minus beta py square upon 2m times integral 0 to infinity dpz e raised to minus beta pz square upon 2m times integral dx integral dy integral e raised to minus beta mgz dz. This is from 0 to L, and this thing, it is the cross sectional area. If you integrate this, you will get the cross sectional area. So Z becomes, Z is equal to A by h cube. Now this integral here, this is in the format integral e raised to minus ax square dx 0 to infinity. This is a standard integral and it is equal to root of pi by a. Therefore we have here, instead of a, we have beta divided by 2m. So the integral evaluates to root of pi divided by beta upon 2m. This is equal to root of 2 pi m upon beta. The integral in y and the integral in z is also similar, so they also produce root of 2 pi m divided by beta. Therefore we can cube this. So we have 2 pi m divided by beta the whole raised to 3 by 2. Now integral dx integral dy is a, which is already calculated. Remaining is integral 0 to L e raised to minus mgz beta mgz dz. This is equal to a divided by h cube 2 pi m divided by beta the whole raised to 3 by 2 1 minus e raised to minus beta mgl the whole divided by beta mg. Now we will take ln of this. Ln of z is equal to ln of a minus ln of h cube minus plus 3 by 2 ln of 2 pi m minus ln of beta plus ln of 1 minus e raised to minus beta mgl minus ln of beta minus ln of mg. When we take derivative, all constants will contribute nothing. Therefore we have average energy is equal to minus del by del beta of ln z is equal to minus of this term is constant, it will not contribute. This is also constant, this is constant, and this is constant as well, so these terms will not contribute. From the remaining terms we have 3 by 2 minus 1 by beta, it is the derivative of this term, and 3 by 2 is from outside. Derivative of this term is 1 divided by 1 minus e raised to minus beta mgl. When we apply chain rule, we have to take derivative of this right now, so that will give you minus e raised to minus beta mgl times minus mgl. And from this term we have one more minus 1 by beta, so average energy is equal to 5 by 2 beta minus mgl e raised to minus beta mgl divided by 1 minus e raised to minus beta mgl. So this is the average energy. Now let's check the behavior of average energy when t is tending to 0. When t tends to 0, beta is equal to 1 by kt tends to infinity. This implies e raised to minus beta mgl tends to 0. This implies the term mgl e raised to minus beta mgl divided by 1 minus e raised to minus beta mgl. This is tending to 0 and this is also tending to 0. Therefore this term will be approximately equal to 0. Therefore average energy is equal to 5 by 2 beta. The second term is negligible, and this is equal to 5 by 2 into 1 by kt. This is equal to 5 by 2 kBt. This is the average energy when t is tending to 0, and average energy when t tends to infinity, that we have to find out now. When t tends to infinity, beta tends to 0. This implies e raised to minus beta mgl is equal to 1 minus beta mgl plus beta square m square g square l square divided by 2 factorial minus etc. So when beta is tending to 0, we can neglect all these terms. All this term is negligible. Therefore we have here, this can be approximated to 1, and this can be approximated to 1 minus beta mgl. Then we will get average energy is equal to 5 by 2 beta minus mgl into 1 divided by 1 minus beta mgl. This is equal to 5 by 2 beta minus mgl divided by beta mgl. This is equal to 5 by 2 beta minus 1 by beta equal to 3 by 2 beta, which is equal to 3 by 2 kBt. So this is the average energy when t is tending to infinity. Now the ratio, we need the ratio of CV when t is tending to 0 and CV when t is tending to infinity. This is equal to del by del t of E when t tends to 0 divided by del t of E when t is tending to infinity. So this is equal to 5 by 2 kBt divided by 3 by 2 kBt. This is equal to 5 by 3. So the correct option here is 5 by 3.